Good day, everyone. I am Fernando Barina, and together with my partner, Marcell Risandi Putra, we are honored to present our research title, Comparative Analysis of Traditional Machine Learning and Deep Learning Models for Inflation Forecasting in Indonesia. This research was conducted under the supervision of Dr. Alfi Yusroti Sagia and Sharifa Diana Permai from the School of Computer Science, Bina Nusantara University. This presentation is prepared for the International Journal of Fuzzy Logic and Intelligent Systems (IFJIS). To begin, let's discuss the background of our research. As a crucial macroeconomic variable, accurate inflation prediction is fundamental for Bank Indonesia to formulate and execute effective monetary policies. However, Indonesian inflation is characterized by high volatility and nonlinear dynamics which are notoriously difficult for conventional linear models to capture. Furthermore, existing research still lacks a comprehensive comparison across all these three model categories, especially in handling the post-pandemic structural shocks within the Indonesian context. Our dataset faces three main challenges: high volatility with sharp fluctuations, nonlinear dynamics that require complex modeling, and the structural shocks from the major events like 1998 Asian crisis, 2008 global crisis, and 2020 COVID-19 pandemic crisis. These factors combined mean we cannot rely on the simple linear models and must use a more robust analytical approach. Based on these challenges, our research objective is to evaluate and compare these three model categories for forecasting Indonesian inflation rates. By doing so, we aim to provide key insights for policy formulation and encourage the development of adaptive machine learning or deep learning methods to better manage the complexities of our Indonesian economic data. Moving to the literature review, our research builds upon several key studies. Traditional models like ARIMA and SARIMA have been effectively in predicting stable data across various sectors. However, recent studies highlight that external factors such as global supply chain pressures now play a more significant and persistent role in driving inflation. Our study bridges this gap by directly comparing these established traditional methods with modern machine learning and deep learning approaches to better handle the complex anomalies in Indonesian economy. Now, let's walk to our complete research workflow. Our methodology follows a structured pipeline starting from data preparation and splitting to the model building phase. We are evaluating four distinct approaches: baseline time series, ARIMA or SARIMA, machine learning, SVR, XGBoost, LASSO, standalone LSTM, and LSTM hybrid model. Each model is rigorously tested in the evaluation stage using RMSE, MSE, and MAVE metrics to identify the most accurate forecasting model. Moving on to the data collection. For this study, our research utilized monthly Indonesian inflation data from BPS spanning from 1979 to 2025 with 561 data points. The dataset tracks specific attributes including the month, year, and monthly inflation rates, where the positive value indicates inflation and negative value indicates deflation. The scope is strictly focused on Indonesian national inflation and utilizes Python for model comparison with excluding other macroeconomic indicators. In the pre-processing stage, we use label encoding for time features and handle anomalies by normalizing S3 spikes, such as the 1998 inflation crisis, to maintain model stability. Our data splitting follows a strict chronological order to prevent the data leakage. We utilize a 80-20 trend test split for traditional and machine learning models, while implementing an 80-10-10 split trend test and validation for our deep learning approach to ensure better hyperparameter tuning. In this step, our study compares 4 distinct models categories to identify the most accurate forecasting approach. We utilize traditional models such as ARIMA and SARIMA and machine learning model techniques LASSO, SVR, XGBoost. Furthermore, we implemented deep learning through LSTM and various hybrid architectures such as LASSO LSTM, XGBoost LSTM, and SARIMA LSTM to capture complex data patterns. To determine the superior model, we employ these 3 standard evaluators, RMSE, MSE, and MAPE.
Let me introduce myself. My name is Marcell Risandi Putra. Before going into the results, this slide explains the notation used. Base value refers to baseline parameters, while base value indicates tune parameter. For hybrid models, base and base LSTM show whether the LSTM component was tuned or not. Next, we move to traditional model. We start with ARIMA and SARIMA. ARIMA fails to track inflation dynamics, producing very large errors. SARIMA improves slightly by modeling seasonality, but still struggles with volatility, as seen from the high RMSE values. Next, LASSO. LASSO introduced regularization to capture dominant linear patterns. Compared to traditional models, it significantly reduced error. However, its prediction remain limited because inflation patterns are not purely linear. Next, SVR. SVR capture non-linearity relationship using kernel methods. This improves stability compared to LASSO, but still SVR still struggles with long-term temporal dependencies in inflation data. Next is XGBoost. XGBoost leverages ensemble learning to model nonlinear interaction. While it performs better than traditional models, the limited feature space of univariate inflation data restricts its performance gains. Next, we move to LSTM. LSTM model delivers the strongest standalone performance. After hyperparameter tuning, LSTM achieves the lowest RMSE and MAPE. This shows LSTM ability to learn long-term dependencies and adapt to regime change to inflation data. Next, we move to hybrid model. This hybrid combines SARIMA seasonality with LSTM temporal learning. However, the structural mismatch between linear SARIMA outputs and non-linear LSTM dynamics leads to very poor performance. Next, LSTM combined with LASSO slightly improves over LASSO alone. LSTM handles temporal patterns, while LASSO refines linear residuals. Despite improvement, the hybrid does not outperform standalone LSTM. Next, LSTM combined with XGBoost perform better than most models except pure LSTM. XGBoost refines nonlinear residual patterns after LSTM prediction, resulting in strong but still secondary performance. And this is the table summarizes the overall model ranking. LSTM rank first, followed by LSTM XGBoost and LSTM LASSO. Traditional models rank last, confirming their limitation for volatile inflation forecasting. In conclusion, LSTM is the best performing model for forecasting inflation in Indonesia. Although its prediction appear conservative, it generalizes well and is valuable for hybrid models. In future research, should integrate macroeconomics variables to further improve prediction accuracy. The following are all references used in this paper. Thank you for your attention. This presentation highlight how deep learning, particularly LSTM, provides a strong approach for forecasting inflation in Indonesia. I appreciate your time.